My name is Johan Hattne. Up until recently, I held a postdoc position working with Nick Sauter on cctbx.xfel. So what I'd like to talk about in my talk is it's a bit different from what we've seen before. I'm going to repeat a lot of what we've seen before about cctbx.xfel. But what I'll try to do is give an insight into the history of the development of cctbx.xfel, how it came to be what it is today, why certain things were done in a certain way, and sort of tie in with what Anton said during his talk, that everybody should write their own indexing algorithm. This is sort of how we wrote our own indexing algorithm, except it's the whole it's actually the whole software suite. So when I arrived in the lab, this is what we had. We had beam time in 66 days. We had 2 software developers, and that's really a bit of an overestimate because one of the software developers had no idea about Python programming, nor knew very much about XFEL. So it's really rounded up to the nearest integer. We did have access to Piana, the Slack written framework to access the data that we would be seeing once it became time for our experiment. It would also sort of provide an interface to the machine and to the kinds of parameters that we needed to extract. We did have Label-it, Nick's processing toolkit, and we did have the cctbx, the computational crystallography toolbox, and one sample data set. And it turned out that actually having Piana, Label-it, and this, in our case, was crucial in order to accomplish this task. That and combined with one of the set developers actually had a plan of how to go about things. Right, so the first thing then is we looked at the sample data, and as has been mentioned before, trying to extract the image, or the images that we were going to process, which is not, at first at least, a trivial task, because you basically have a blob of bits, and how do you arrange those to sort of represent the image. Now, this is functionality, much of which was provided in Piana, and we went to talk to the developers at Slack, and after some time we were able to come up with something like this. Now this is the CSPA detector. We've got, again, the 4 different quadrants, and we can, they're color-coded here, these sensors, by how they're laid out in the stream, and we can see that these quadrants are symmetry related to each other. This one is 90 degree rotation of that, which is 90 degree rotation of that. So when we got into this stage, we were actually sort of confident, because this looked like the photographs of the actual detector, we were confident that we were extracting the data in the right order. We're not flipping things randomly around. And that was the first big step. We, of course, wanted to verify this for ourselves to actually sort of replace all these colors with actual data. And when we did that, we chose not to look at just one single image, because that first sample data set we had wasn't particularly strong. So introduced this idea of looking at composite images, where it summed up a whole lot of different images. What we would have expected to see in that case were concentric rings. And it turns out that it wasn't, because we had to, that initial arrangement of all these sensory elements wasn't precisely correct. Now, we didn't, I think in hindsight it's fair to say that we didn't realize at the time that this metrology problem, as we now call it, didn't appreciate the amount of time we could sink into that and the importance this would have for the processing further on. But also being some computationally oriented people, and seeing this, we figured that we can write something that automatically does this. Given an image like this, it should be able to correct things, and it sort of kind of did in a way. There was an iterative procedure that was trying to look for these rings, and then trying to arrange the height such that these rings were concentric. What's shown here is that the error in that function as a function of the iteration, and we can see that it converged. Problem was that it converged to something that had was only vaguely related to what we would have expected. So given the time constraints that we had at the time, we abandoned this, at least, or put it on the shelf, at least for the time being, to maybe take it back at some later stage. So instead what we have, and you've seen the slide before, there's something that Nick then wrote up, to look again at these composite images and overlay a ring pattern. And that ring pattern could be arranged such that it would also tell you something about the distance of the detector. So basically in one procedure you could arrange the quadrants such that the rings are concentric, arrange the distance such that the location of the rings match what you would expect from the particular sample that gave rise to those rings. So that's really only the first step in this sort of procedure of calibrating the metrology, because it turned out that while this is enough to get stuff indexed, I mean, basically it's good enough to get a foot in the door, it's not quite enough to do things accurately. And again, you've seen the slide before, but what we did next then is to take these images, index them, and then compare. Where are the observed spots, and where does the indexing algorithm predict that this spot should be? And do that for lots and lots of images, and look at the residuals, the vectors for any one particular element of the detector. This one chosen there. We can see that, and you get a scatter plot. And it looks pretty good in this case. Maybe one should have sort of moved this whole little element a fraction of the pixel to the left. But doing this analysis, that was the kind of corrections that we could apply after that. And this really allowed us to not just index and process stuff at low resolution, but to sort of push it towards high resolution. So the procedure that we had then was really something that, starting from the initial metrology, basically what Slack, after they had done the measurements on the detector, would tell us was correct, we could nudge things around a tiny little bit and end up with a slightly refined metrology, and we could use that to do indexing. So indexing depends on metrology, and then we go back and determine new metrology based on predicted and observed spots. So then you've got the case where your metrology determination depends on indexing. So it's really sort of circular dependencies. So what we can hope to arrive at using this approach is to a fixed point, and where stuff doesn't change anymore, no matter how much we cycle. And then hope that that particular fixed point actually corresponds to the solution we're after. And turned out that it converges pretty fast. I mean, this is one of the very first plots where the translational correction is shown in red, in pixels, and rotational correction in green, there. I can see that after just a handful of iterations, we're done to the point where we can't really improve it much. That was all fine, and I think we didn't until much later realize the importance that all this would have on the process data. And so this is from the publication that came out earlier this year. Nick talked about this, but and since he has, maybe just reiterate that if we're as much as one pixel off in how we're placing these things, we tend to lose, or in this particular case, we lost a third of the high resolution images. The degradation in considering just all images is a bit slower, and what this then does suggest is or maybe confirm that the way we have been working with metrology is starting from looking at just the quadrants close to the beam center and sort of working ourselves towards the outer high resolution sensors, that makes sense, because the high resolution parts of the detector are more sensitive to disturbances in the metrology. So another thing that came out of this sort of early work with the detector was a different way, or well, we didn't really have a way before that, but the way to think about how this was arranged. And the way we thought about that then is that we thought the detector, sort of an abstract object or concept, the whole thing, the thing that records our intensities. Now, that detector is related by some rotation and a translation to a reference point. Inside the detector, we've got 4 quadrants, or panels, as I recall them, each of which is related by rotation and translation to the reference frame of the detector. Inside the panels, we've got sensors, 8 of them, and each sensor would have an ASIC. So the idea was that a sort of hierarchical way of thinking about the detector could help us in dealing with the metrology issue. So here's just another representation of that. If we're looking at the very lowest level, where we have some mock ASIC with pixels that aren't even square in this case, but and you would address the pixels by coordinating the fast scan axis and coordinating the slow scan axis. For that, then it's related to the coordinate, the three-dimensional coordinate system of that particular element. What's not shown is that this coordinate system will be related to the coordinate system of the parent, and so on, all the way up to the detector. Didn't really go very much further with that idea until Aaron came along and took all this and did a whole lot of work on refining these ideas and managed to formalize it and then put it into the language of CBA, which is something that is very exciting about that. Right, so this stuff about the methodology we've largely seen before. Another thing, I mean, as you're working as a developer on these things, it really helps if you can try out things fast. I mean, you don't really want to be in a situation where every time you change something, you want to see the effect of that change, you'd have to run it overnight. So, and one thing, or one way to speed things up is, of course, to write better algorithms, but that then takes time. So an alternative to that is to just throw more computational resources at the problem. And with these kind of things, we are in a good situation of having an embarrassingly parallel problem, because basically every diffraction image can be processed completely independent of all the other diffraction images. And what that means then is that, in principle, the more processors we throw at this problem, the faster we can push it through. That was the idea. And this was made even easier for us because PyANA, the stack provided framework, already had this functionality in place. So the way this would work is that we would take an XCC stream, we would feed it to PyANA, and PyANA would then split out the frames inside that stream to different processors. Inside every process, we would apply hit finder, based on this spot finding, and then index and integrate each image, and we can do that in parallel. So when we actually did this, and by now we had started to become users at NERSC, the National Energy Research Scientific Computing Center. So when we actually tried this out in practice, it turned out that the speed up we were getting wasn't quite as good as we had expected. So if we're considering a tiny stream with 6 frames in it, the first one would be hit with the diffraction spots on it, and with 3 blank images, maybe because the jet containing the sample was not hit at all, or maybe there were no crystals in the jet. Another hit and a blank, and so on. Right, so processing a hit takes much longer time than processing a blank. Because, well, if it is a blank, then you're not even going to bother trying to index and integrate it. So if we were to take this data stream and process it on 2 processors, we would ideally hope to get something like this, where the first processor processes the hit, and then you would spend, the 2 blank images would go to the second processor, and so on. Third blank goes back to the first, which has become free after processing the hit. The point here really is that both CPUs are fully utilized all the time in the situation we had hoped for. And it turned out, and this was really stuff figured out by David Skinner at NERSC and Andrei Salnikov at SLAC, that this was not happening. Because what happened is that it would really round robin these events to the different processors. So what you're noticing here, we have, that's the first image, the second, and the third, fourth, fifth, sixth. So, and we have this idle time. And it doesn't look so dramatic if we're just considering 6 events, 2 out of which are hits, but on large real data sets, this was really degrading multiprocessing. But the difficult problem, or the difficult part about this problem was really to get to this stage where we could identify what was going wrong and then it could be fixed very quickly. So then we started to see the kind of speed up that we were expecting. And it's not always linear. And the reason for that is that it really depends on what we're doing with the data. And there's sort of two extreme cases are illustrated here. So above here is an averaging operation. So basically, we're taking the data stream, we're extracting the image data, summing it up, and going to the next frame. So there's very little in terms of actual computation involved. And what this means, if we're doing this, is how fast we can push this through really depends on how fast the disks can give us data. It will depend on not just the actual disks, but also on the interconnect between the place where between the file servers and the processing units. At the other extreme is if we're actually trying to process data, which is really CPU intensive. So what would happen? I can say what would happen here is that basically after we're using 4 CPUs or so, we don't really gain anything more because we're bound by I/O. However, for processing, that is not the case. Basically, the more processors we throw at the problem, the faster it goes. So doing a bit of back-of-the-envelope calculations, if it were hit finding, if that basically determining whether the image is a hit or not, if that were to take 1 second per image, and we assume that indexing and integrating, so fully processing an image would take 10 seconds per image, and we assume a run where frames are recorded at 120 hertz for a 2% hit rate, you would need 380 CPU seconds to process 1 second of raw data. And this is beyond what SLAC could offer us at the time. I mean, SLAC had just below 500 cores at the time, but we for sure would not have been allowed to hog all those ourselves. Right, so but since we were at NERSC already and sort of extending the collaboration with the people at NERSC, figured that NERSC has tens of thousands of cores, or lots and lots of cores. So could we be able to do the processing there? And came up with an arrangement that would actually allow us to do that. The only issue then is that NERSC, of course, is not SLAC, and the data was recorded at SLAC, and NERSC is in Oakland, it's not very far, but it's a bit of a transport issue. So not only then did we come up with an arrangement where we had reserved cores at NERSC, but we also got a bit of the link between SLAC and NERSC dedicated to us in order to ensure that the transfer between SLAC and NERSC would proceed in a timely fashion. So here is, this is the experiment where we actually did that. So 5 shifts, basically 5 12-hour shifts. What's shown in blue is the data as it arrived on the data acquisition system at SLAC. From there, it's transferred to an offline system, also at SLAC. This is in red. And you can see that except for the second shift, the blue and the red almost overlap, and technical issues during that shift, which prevented that from happening. Then in this yellow-brownish color is the volume of the data as it arrived at NERSC. Yeah, so shift 3 was a bit of a disaster, but by that time the experiment as such was actually running as we had hoped from the start. So basically shifts 4 and 5 are sort of running at capacity. And what we can still see is there was a bit of a lag in the transfer to NERSC, but it did work, and overall it was a huge success and a fine example of what can come out of these larger scale collaborations. So everything I've said so far it has either been seen before or said before. So I'd just like to switch for the last part of my talk to something completely different, which has to do with the position I'm currently in. Right, so here are light-assign crystals. The scale bar there, so that they go up to a level approaching 100 microns on a side. Now with XFELs, we can study these because we get very bright pulses, and the pulses are also very short. So yeah, we circumvent radiation damage by doing when we're doing an XFEL experiment. An alternative to looking at these things using X-rays is to use electrons, and we can do that because electrons interact much more strongly with matter than X-rays do. So whereas the radiation damage issue was sort of circumvented in the XFEL case, it wasn't entirely clear how to deal with that with electrons. So that's shown here. We're seeing, how much dose can a typical sample withstand before it's ruined. For inorganic materials and polymers and biomolecules, somewhere between 5 and 20 electrons per Angstrom squared. So the question really was, if we go much below that, will we still be able to see the kind of data that we need to process this and process it as a sort of regular crystallographic diffraction experiment? And it turned out that we can. So this is a sample image from lifetime, and the whole data set, where the dose sort of accumulated of the whole data set was around about 0.1 electrons per Angstrom squared. Now, so that basically shows that we could do that without accumulating a whole lot of damage. In practice, so the way it's done is that we have the sample, we deposit it on an EM grid, used for transmission electron microscopy. This is about 3 millimeters on the side, the diameter is about 3 millimeters. Put that grid, after freezing it and lotting it into an electron microscope and screen for crystals, they look like that, and then expose them just as we would have done in the X-ray case. Now, one big difference there is that, and this is something that often comes up with talking to crystallographers about these things, is that the kind of wavelengths that we're looking at with electron crystallography are a lot shorter than the wavelengths that we would be seeing with X-rays. So that's shown here. There's the light sign diffraction image again, collected on a home source. So a cartoon of the lattice, and then the evil sphere, and where the evil sphere is intersecting the lattice, that gives you the spots that are in the diffraction condition, which you then record on the image. So in the X-ray case, we actually sample the lattice in 3D. Now the wavelength in the electron case is so much smaller that the evil sphere is essentially flat, and instead of seeing sort of a 3D part of reciprocal space, we just see a plane or line. So what that means is it's actually impossible to index or to determine the parameters of this lattice given just a single image. However, because we thought this low dose, we can collect more than one image from each crystal, and this is really where this is starting to get different from the X-ray case. Another way this is different from the X-ray case is that because we're shooting electrons and not X-rays, we can do all kinds of optics, we can focus and we can do all kinds of optics on that beam. And the consequence of that is that if the microscope isn't calibrated properly, then you may see things like this. This is the beam center, and it's moving or oscillating throughout the collection of the data set. And here is, so the worry there is that if this oscillation is too much, then the processing software could not compensate for that anymore, and we'd lose processing results. Now, it does turn out that basically the same algorithms that we used or those ideas that we had in the beginning to determine the position of the quadrants on the CS pad can be used to detect and correct for the movement of the beam center. And just to outline that, the way that works here is diffraction image. Now, if we were to assume that the beam center is somewhere here, or somewhere off the center, and then we look at the average and the variance in rings around that sort of trial beam center, then if we're very far off, then we see something like this. We put the average intensity in those rings in red, the variation in green. If, on the other hand, we're looking at the correct beam center, or we're close to the beam center, then that distribution, or those distributions look something like that. Now, the idea is really that we can construct a target function out of that idea, that starting from some initial guess of the beam center, so works its way towards the correct beam center. So those issues can be detected and corrected for. So further refinement of that technique. So I mentioned that we can, due to the low dose, collect more than one image of the same crystal, shown here, we're sampling 7 different times. And that's seen here. I mean, basically what we're having is a series of still shots, just like what we got in X-ray crystallography. An alternative to that is that we can actually do what we're doing with the oscillation method at synchrotrons, where we're continuously spinning the crystal and recording actually moving. So those different views of the data are contrasted in these two movies that are now both playing, whereas you can see that here it's a lot more jumpy. Spots appear and disappear. Here they sort of fade in, fade out. Now the implication of that is that instead of recording frames where every intensity is partial, we have a sort of much more complete picture of the intensities in the case where we're using continuous rotation. Right, yeah, so it works, is what this slide says. We just recently saw went beyond lysozyme and looked at catalase, which has been, sort of has a long history in electron diffraction. And, we're able to solve the structure from catalase to 3.2 functional solution, phased by the molecular replacement. Density looks good. So, last slide, contrasting then XFEL stuff to micro D, as we call this method. We're looking at tiny crystals. Most of our intensities tend to be partial, and processing is really finicky. And we've got to deal with tricky hardware. Now, in the XFEL case, the hardware issue is tricky because everything is custom built. Aaron was talking about this, and Nick as well. In the electron diffraction case, it is difficult because we're really using an instrument that was built for something completely different than what we're trying to use it for. We get data in a surprisingly similar format. It's streams that are chunked at regular intervals. And it's different because we actually have to use Python, at least for now. It's also a whole lot less demanding on the processing requirements. Basically, I can look at this data and process it on my desktop. And I think also maybe tend to be a lot less collaborators or authors on anything. Right, that was it. I'd like to acknowledge everybody I've worked with, both the XFEL stuff and now more recently with the MIP stuff, and CCI, Paul, and from supervisor Nick, and the Yashandra group. I didn't really talk about that, but that's how we got into this whole business of XFELs, Vitor and Junko. The collaborators at Diamond were responsible for dials. Andrew Leslie, Gary, and the LMB in Cambridge, people at SLAC, and collaborators in Stanford, Mona and Oliver, I think will be giving the next talk. Right, and thank you for listening.
I think what you say about is correct about the TNE, but there is a thickness limit on those due to the multiple scattering curve.
Yes.
And of course, it works very well for 2D crystals, one molecule thick.
Yeah.
Our calculations suggest you'll get about 10% error at 200 angstrom thick. But again, it's going to depend on the extent to which you use molecular replacement. You can afford to have pretty bad quality data.
Yeah.
Electron intensities and still get a map as long as you use a good modeling for the database.
Right. So I think
it'll work fine as long as it's thin enough. And thin enough probably means a few hundred angstrom.
Right. No, I mean now with the molecular, we're aware of those issues, and with the molecular replacement, we've done all kinds of tests in attempts to verify that what we're looking at is actually real and not just an artifact of the molecular replacement. But in the future, I suppose that one would really have to apply some kind of correction for these effects during the processing of the data. Yeah.
With the data obtained for reception determine the sufficient for the novel structures?
So this is something that we're actively working on at the moment. I mean, we haven't, we've made some progress, but there's nothing published on that yet. But that's something that we're very actively looking into.
Your estimate? Yes, probably. Because
I would say so, yes. But I mean, until it's actually done and sort of squared away, I shouldn't really promise anything. But,
And then maybe possibly use that as an electron. That's what it suggests.
No, I mean, so our first angle of attack is
that was not my question. I don't.
Yeah.
I won't.
No, and I think also, I mean, maybe since we're working with electrons, that gives us some completely different ways of phasing.
Let's thank our speakers again.